Let's have a brief look at the changes in coding paradigms over the last 40 years. Specifically, we're going to look at the change from synchronous to asynchronous execution. When computer applications supported a single user with a simple text-based interface, programs worked by executing code sequentially, that is, line by line. Each time a function is called, program execution waits until that function returns, and then continues with the next line of code. This is synchronous programming. In this example, we can see that after asking for an I/O input, so we were asking for a name, the program pauses until you press the enter key and the next line of code is then executed. With synchronous programming, the sequential line of processing makes reading and following the code an easier and more predictable task. Graphical user interfaces are naturally multimodal. This means that the user can do many things with the user interface. I press buttons, type in text fields, switch windows. The user interface is not waiting for a single input. There may be many different types of input. The initial approach to handling user events was an event loop. The event loop is a perpetual loop that monitors a range of UI events in sequential order. If the number of events to be monitored and the length of time to respond to each event exceeds the processing abilities of the computer, you might be able to notice waits in your application while it tries to process each iteration of the loop in a timely manner. With an event loop, the program is still in full control. It constantly loops and checks for new events. When a new event occurs, it checks the type of event and executes a response synchronously. Because event loops became the standard way to process events, the approach was abstracted to event handlers. Event handlers are an extension of the simple event loop that processes each event in a stack-based order, being first in, last out. It retains the event loop, but includes an event table and an event queue. The event queue is similar to the main event loop in that it stacks up a number of waiting events. Because the load of managing this event stack is taken on by the event queue, the main event loop can proceed with limited interruptions. This is an asynchronous process, as the main loop no longer controls the execution of the events in the event queue. Asynchronous programming using traditional event handlers can be significantly more complex than synchronous programming and can introduce a number of issues. One issue is maintaining a consistent state. For example, two different event handlers may modify views and data independently, resulting in the view being inconsistent with the data. Reactive programming is programming with asynchronous data streams and the propagation of change. This is event handlers on steroids. A stream is a sequence of ongoing events ordered in time. A stream can emit three different things: a value of some type, an error, or a completed signal. We captured these emitted events asynchronously by defining a function that will execute when a value is emitted, another function when an error is emitted, and a further function when completed is emitted. Reactive programming manages asynchronous data flows between sources of data and components that need to react to that data. In imperative programming, A equals B plus C would calculate the result of B plus C and store it in A just a single time, and would no longer be affected if B or C changed in values unless the line of code is executed again. In reactive programming, A equals B plus C would continually update the value of A as B or C changed. We have encountered binding in Angular. Binding is an example of reactive programming. When we include a component variable in a template, Angular binds the variable. When the variable value changes, the HTML would automatically update. This is a specific example of reactive programming. A software design pattern is a reusable solution to a commonly occurring problem. It is similar in concept to an algorithm, but generally is focused on the software architecture rather than the procedural execution. Software design patterns were popularized by the Gang of Four in 1994. Common design patterns used in object-oriented programming, proposed in the Gang of Four's design patterns book, included 23 different design patterns, including factory methods, singletons, decorators, iterators, and observers. The observer pattern is used to allow a single object, known as the subject, to publish changes to its state. Many other observer objects that depend upon the subject can subscribe to it so that they are immediately and automatically notified of any changes to the subject state. The pattern gives loose coupling between the subject and its observers. This means that the subject holds a collection of observers that are set only at runtime. The actual functionality of the observers and their use of the state data provided by the subject need not be known by the subject, thus the term loose coupling. The observer pattern is also widely used in user interface development, particularly with data binding functionality. In the observer pattern, the subject or publisher of the data broadcasts any changes to the observers which had put their hand up and subscribed with the subject to get notifications of any change. Angular uses RxJS library to provide the functionality to implement the observer pattern. We'll run through an example here where we create our own subject and observer functionality to see what is happening below the skin of RxJS. To create an observer pattern, users will require a subject and an observer. The subject will contain a list of observables as well as the value that can be changed. When the value is changed, the subject will notify all of the observers in this list. Here we have our subject class. It contains an array that will hold the list of observers that it will need to notify. It contains a subscribe method that adds a new observer to the observer array. A change value method is also available to update the data of the subject and then notify each of the current observers of the change by calling a change event on each of the observers and passing the new data value to that event. The observer object has its data and a change method to respond and do something with the data coming from the subject. So here a subject is created and the data is changed to initial value. The two observer objects lodge their interest in the subject by subscribing with the subject so that they can get notified of any data changes with that subject. Here, the two subjects do their subscribing. The subject updates its data. Here, a third observer object is created and it lodges its interest with the subject so that it can be notified of any changes with the subject. The subject updates its data and notifies all three observers. In the previous example, all of the observers did the same thing because they used the same class which had the changed function. In reality, each observer will respond to the changed message differently. One way that we can support different types of observers is to use an interface. An interface is like a class but with no implementation. Interfaces define properties, methods, and events that are the members of the interface. Interfaces contain only the declaration of the members. The members are the properties, methods, and events. It is the responsibility of the deriving class to define the members. Having interfaces often helps in providing a standard structure that the deriving class should follow. Below is the observer interface. Note that it is declared as an interface and not as a class. It is similar to the class, but the method has no body. The interface indicates what method an implementing class will implement. We can now make as many observer classes that we like that implement the observer interface. If a class indicates that it implements an interface, it must provide implementations for all of the methods in the interface. In this case, each observer must implement the changed method. The actual implementation of the change method can be different for each observer. Using the same example as before, we can see that the output is different because each observer is outputting a custom message for its own changed method. Note here that the subject class didn't change. The observer interface is a type, and we can use it where we might use a class. A class can implement multiple interfaces. In this example, the interfaces of add and subtract define the shape of these classes, and the arithmetic class provides the implementations of these methods. If a class specifies that it implements an interface, it must implement the methods of the interface, otherwise it will generate an error.